Good morning, friends. Now, in this session, we are discussing the classification of fluids and the concept of surface tension. In the earlier session, we were discussing about the basic properties of the fluids like mass density, weight density, specific volume, and the major property of any fluid, so that is viscosity. So now Newton is the scientist who has given the law of viscosity. So it states that the shear stress tau on the fluid element layer is directly proportional to the rate of shear strain. So tau is here the shear stress, and du by dy is the rate of shear strain. So tau is proportional to du by dy. So mu is the proportionality constant. So that is also called as coefficient of viscosity. So mathematically we can say that tau is equal to mu into du by dy. So the units of viscosity is that so it is in Newton second per meter square in SI system. So this Newton per meter square is also called as pascals. So it is called as Pascal into seconds. So Newton second per meter square. So pascals seconds. So in MKS system, the unit of viscosity. So here the force is instead of expressed as Newton, it is expressed as kg force. So it is kg force into second per meter square. So in CGS system, the unit of viscosity. So instead of force expressed in newtons or kg force, it is expressed as dyne. So it is dyne second per centimeter square. So in SI system, so the unit of length is meter. So in CGS system, it is in centimeter square. So that's why it is dyne second per centimeter square. So also this entire dyne second per centimeter square will be called as poise. So 1 poise is noted as 1 by 10 of Newton second per meter square. Now coming to the classification of fluids. So the fluids will be classified into the following 5 types. So the one is the ideal fluid. Then we have here real fluid. So then Newtonian fluid, non-Newtonian fluid, and the ideal plastic fluid. So in x-axis we are showing the ideal fluid. On y-axis we are showing the ideal solid. So x-axis is representing the velocity gradient, so that is du by dy, and the y-axis is representing the shear stress here. So we'll see now one by one. So ideal fluid. So it is the one which is incompressible and having no viscosity. So we can call the fluid as ideal when it is incompressible and having no viscosity at all. So that fluid will be called as ideal fluid. But all the fluids under the sun, is having some amount of viscosity. So that's why we say that ideal fluids are only imaginary fluids, because all the fluids existing in the world are having some viscosity. Now real fluid, a fluid which possesses viscosity is known as real fluid. All the fluids in practice are real fluids. Then Newtonian fluid. So the name itself says the fluid which obeys Newton's law of viscosity, that is a real fluid in which the shear stress is directly proportional to the rate of shear strain or velocity gradient, is called as Newtonian fluid. Example: water, air, so thin motor oil. So whether it is a liquid or gas, so it will be called as the fluid. So which obeys Newton's law of viscosity is called as Newtonian fluid. So then non-Newtonian fluids, a real fluid where the shear stress is not proportional to the rate of shear strain, that is the velocity gradient, such fluids will be called as non-Newtonian fluids. That is the fluids which are not obeying Newton's law of viscosity. Example, toothpaste. So even if the load is remote, so the toothpaste tube, so it is already undergoing deformation once the load is applied, even after the removal of the load. So the paste which gets compressed here, so right. So then the ideal plastic fluid. So a fluid in which the shear stress is more than the yield value, and the shear stress is proportional to the rate of shear strain, that is the velocity gradient, is known as ideal plastic fluid. So examples, sewage sludge. So here the nature of the graph will show what type of the fluid it is. So here, so Newtonian fluid. So as here my stress is directly proportional to the velocity gradient, so that is du by dy. So as this velocity gradient increases, the shear stress induced on the fluid is also increasing gradually. So Newtonian fluid is shown here. So non-Newtonian fluid, so there will be no proportionality between shear stress and the velocity gradient in case of non-Newtonian fluid. Then coming to ideal plastic fluid, so here the proportionality between the shear stress and the velocity gradient will not start exactly here where the x-axis and y-axis meets. So it starts from here. So the ideal plastic fluid. So ideal fluid is shown on x-axis. So that indicates that so there will be no shear stress at all. So but such fluids will not be existing in nature. Surface tension. So the name itself says that the tensile force acting on the surface of the liquid. So now we are considering a liquid here, so that is having a contact with the gas, right? So it is on the surface between two immiscible liquids. Suppose if I consider oil mixed with the water, so these two are the immiscible liquids. So at the intersection of the two liquids, so there will be some tensile force acting. So this tensile force, right, will be called as the surface tension. So this surface tension is denoted by the Greek letter sigma. So the SI unit of surface tension is in Newton per meter, and in MKS unit it is kg force per meter.